Buried beneath a single mound of earth lies a metropolis up to 50 times its size, built with no blueprint, no leader, and secrets that rival human engineering. The masters behind these vast underground cities are tiny ants, yet their collective genius has left scientists astounded. What invisible rules guide millions to construct such intricate worlds? The answer defies what we thought possible. At first glance, only a mound of loose earth hints at the world below. Ants appear and vanish in a steady stream, each carrying a grain of soil from the darkness beneath their feet. Around the entrance, a ring of excavated earth steadily expands. In some species, this mound can reach the size of a dinner plate, over 1 square meter across, built grain by thousands of tiny workers. The entrance mound is more than just a pile of dirt. Its shape channels rainwater away and helps maintain the delicate balance of temperature and humidity inside. The soil itself holds clues. Fine particles, sorted and stacked, reveal the careful labor that continues unseen. Every ant that surfaces adds to this evolving structure, yet the real marvel lies out of sight. These surface signs are only the faintest hint of the vast, ordered labyrinth hidden below, a city whose true scale is waiting to be revealed. A single experiment would change everything. In the early 1990s, biologist Walter Tschinkel poured liquid plaster into an active fire ant nest, letting it flow deep underground. Days later, the hardened cast was carefully excavated, revealing a sprawling network that stretched 55 square meters, larger than many studio apartments. The cast captured not just tunnels, but hundreds of distinct chambers, each with a purpose. Shallow brood chambers clustered 30 to 45 centimeters below the surface, where warmth accelerates growth. Deeper still, between 60 and 200 centimeters, lay the fungus gardens, humid, stable, and essential for the colony's food supply. The nest's layout echoed the zoning of a city, with storage, nurseries, and waste sites set apart for survival. Tschinkel later reflected that he realized he was sacrificing a living system for scientific insight, but that the revelation of such beauty justified the cost, so long as it deepened our appreciation and respect for these master builders. The cast offered undeniable proof. Beneath a patch of earth, ants construct a metropolis. Yet one question remained: how do they achieve such organized complexity grain by grain? There is no architect beneath the soil, no overseer drawing up plans, yet order takes shape from the smallest cues. Each ant responds to a world of signals, a faint chemical trail here, the touch of a soil grain there. This is stigmergy, a form of self-organization where the environment itself becomes the blueprint. As one ant deposits a pellet, it leaves a trace of pheromone that lingers for minutes, sometimes hours, fading with time and weather. The next ant senses this invisible mark and is more likely to add its own grain nearby. Pillars rise where signals accumulate, their spacing and size shaped by the rate at which pheromones decay. Too quick, and the nest fills with tiny scattered supports. Too slow, and only a few grand columns appear. When a pillar reaches the height of an ant's body, a new rule triggers. Workers begin to roof over, forming arches and domes. Division of labor sharpens this process. Excavators dig, transporters pass soil along living chains, and stabilizers shore up new walls. Time-lapse studies reveal the result: a living, moving assembly line, each ant following simple rules, yet together building a city whose order seems to arise from nowhere. From fleeting chemical traces and body-length measurements, a metropolis grows, guided not by intention, but by the logic of collective instinct. Deep inside the nest, air moves with surprising force. In a mature colony, vertical shafts and winding tunnels channel fresh air at rates of 10 to 20 liters per minute, enough to refresh the entire underground city every hour. This is not random. The mound's shape, the angle of each shaft, and the placement of chambers all work together to drive passive ventilation, keeping carbon dioxide low and humidity just right. In the fungus gardens of leafcutter ants, airflow is so consistent that engineers have measured steady exchange even when outside winds are still. Architect Yasmin Sabri, who studies natural ventilation, puts it simply: Ada nests ventilate with an elegance that rivals our best designs, yet they are built grain by grain without a single blueprint. But the colony's engineering goes beyond air. Where a tunnel collapses or a gap opens, the ants themselves become living architecture. Army ants and fire ants will form bridges from their own bodies, hundreds joining together, flexing and adjusting as traffic passes overhead. A single living bridge can hold anywhere from 100 to 500 ants, shifting shape as the colony's needs change. These structures are not just feats of strength. They are adaptive, self-healing, and temporary, dissolving as soon as the path is clear. Every detail, from the airflow in a shaft to the living span of a bridge, is tuned for survival. The colony's architecture is not just built, it is alive, responsive, and efficient. Ants do not dig at random. Each tunnel advances as workers select grains of soil with remarkable precision. High-speed X-ray studies show that ants remove grains carrying the least weight, never disturbing the main force chains that hold the tunnel together. As each grain is taken, the surrounding soil shifts, redistributing stress and forming natural arches above the tunnel. The slope of each passage approaches the angle of repose, the steepest pitch before collapse, yet rarely exceeds it. Caltech researchers describe this as building with the physics of sand, not against it. By exploiting these granular mechanics, ants carve stable, self-supporting passageways, grain by grain. After a flood, the colony surges into action. In just 72 hours, over 30% of the tunnel network is rebuilt, restoring lost pathways with astonishing speed. Resilience written in every grain of soil. As cities grow and climate shifts, nature's engineers remind us, true resilience lies in collective action. Even now, beneath our feet, complexity flourishes, built grain by grain, together.